So this will be a relatively short lecture, lecture 11, and I'm going here to cover, to continue the discussion of how we can use derived rules to make our lives a little bit easier in proving more complicated sequence. Today I'm going to focus, so in lecture 10, the previous one, I focused just on cutting in, that's the phrase we use, cutting in old proofs into new proofs. So if you've proved something previously, you can just sort of copy that into your new proof. Today, I'm going to talk about another strategy you can use that it's not itself a new rule. It's a way of thinking about what you could prove with the rules we already have. And this one is called replacement. Okay, so that's the main focus today. And along the way, we're going to pick up a couple other concepts that will be very useful. These concepts are, as you'll see there on the page, logical equivalence. So what does it mean for two sentences to be logically equivalent? And the concept of a subformula of a formula. So we'll actually need both of those concepts in order to make sense of the notion of replacement. So let's start then with the notion of subformula. Okay, so let's take a formula, a sentence. So these are just synonymous in the current setting. When we get to predicate logic in the second half of the course, there'll be a distinction between sentence and formula. In propositional logic, what we're doing right now, these mean the same thing, a formula and a sentence. Okay, so let's just write down a formula. So here's one that I've randomly taken off the shelf. So if P, then Q or R. Okay, so that's a formula. Now, if we were being really logically nitpicky, we could give a precise, utterly precise definition of which strings of symbols actually correspond to formulas. So for example, you know that, hopefully intuitively, something like this, if I wrote right parenthesis P negation symbol and symbol R, that string of symbols in red is not a formula. It's not well formed. It doesn't make sense. So there are some implicit rules in the background here about which formulas make sense. The long and short of it is every formula, every well-formed formula, every legitimate sentence is built up using atomic sentences and then putting them together using connectives in a sequence. Now, actually, we can, for convenience for today, we can think backwards. And that is each formula can be deconstructed into a tree, uniquely deconstructed into a tree. Okay, and what we do is we start with its main connective. That would be the connective that's put in last when it's built up, and start disassembling it from there. So I'll just do that for this formula that we have in front of us, this example. So this formula was put together using if-then, the conditional arrow, with formulas P and Q or R. Notice I don't need to put the parentheses around this Q or R because I'm still following that convention that when I put a formula by itself, it doesn't need parentheses on the outmost bit. As soon as you put it together with another formula, another sentence, it needs to go in parentheses so you know which bits are getting put together. Okay, so that's the first step in the construction tree of this formula. The second step is Q and R. Q and R go together to make Q or R. Then P goes together with Q or R to make the entire formula. Okay, notice the tree itself doesn't show us which connectives were used to put together the bits. We have to look at the formula. So the two branches at the very bottom with Q or R coming together to Q or R look the same as the two branches going together for the main formula there, but they're different. The one on the bottom is or, the one upstairs is if-then. Okay. So this is what actually is called a parse tree. So you computer scientists out there will know this from another context. This is a parse tree for the formula. We're not going to need to be more precise about that. We're not studying parse trees here. And in fact, your intuition about what I'm getting ready to say is probably good already. You probably don't even need to know about parsed trees to know the following. A subformula of a formula is just a well-formed formula, a complete formula that occurs inside the formula. Okay? That corresponds naturally enough to exactly the nodes in the parsed tree. So the subformulas of our original formula here, our original formula, if P, then Q or R, its subformulas are P, Q or R, Q, R. And of course, the whole formula is a subformula of itself. It's just, we might say improperly, a subformula of itself. But the proper subformulas are every sentence that occurs as a unit inside the overall formula. That's the notion of a subformula. Okay, so at this stage, that notion is not interesting for us. It doesn't help us. We're getting ready to see how it will help us. So now we need to go to the next concept for today that we'll need for the rule of replacement, and that is the concept of equivalent sentences. Okay, so every sentence has a truth table. In that truth table, under the main column, so the main column is the column in the truth table under the main connective of the sentence. The main connective of the sentence is the connective that goes in last when you're putting the sentence together. Okay, and we already know, we learned last time the notion of a tautology. A tautology is a sentence that's always true in the main column of its truth table. A contingency is a sentence that's sometimes true, sometimes false. Now we're going to talk about a relation between two sentences. The relation is logical equivalence. Okay, and the definition here is straightforward. If you have two sentences, phi and psi, they're logically equivalent just in case if you write the truth table for the two of them, they always have exactly the same value in every entry. Okay, that doesn't mean that phi is always the same value or that psi is the same value. It means they have the same value as each other. Okay, so for example, it might be something like 0, 0, 0, 0, 1, 1, something like that, etc. Just they always match. So they're logically equivalent. They always have the same truth value. Logically equivalent. Okay, so let me just give you an example. Okay, now if I were to write out the full truth table for these two sentences, I would have 8 rows. I'd rather not do that. I'd rather not write, okay, it's 8 rows and each row has lots of numbers. That would make me sleepy to write all those different zeros and ones, and I probably would get confused at some point. Since I've done that so many times in my life, I'm going to give myself permission instead to reason myself, to convince myself by reasoning that these always have the same value in their truth tables. So here's what I'll do is I'm going to argue that if the first sentence has value 1, true, 1, then so does the second sentence. And I'm going to argue that if the second sentence, whenever it has value 1, so does the first sentence. And what that will mean is they'll always have the same value. Okay, so I'm going to start. I'm going to say, what if the first sentence were true? Okay, what if it had truth value 1 in the truth table? Now, there's several possibilities, but they boil down to either P could be 0, that's one possibility, or if P is 1, either Q or R has to be 1. So those are the two possibilities. So either we have P is 0, that's going to be one of the possible rows where if P then Q or R is true, or we have the rows where P is true and then this disjunction is true, which means one of the two, Q or R, is true. So those are all the possibilities. Okay, now I'll just argue that in both of those cases, the second sentence is true. Okay, in the first case, if P is 0, well, both conditionals on the right are true. So the or is certainly true. Okay, so if P is 0, both of these conditionals come out as true. And so the disjunction of the two conditionals is true. Okay, so the first sentence, if it's true there, the second sentence is true. Okay, on to the second one. What if P is true? Then either Q or R must be 1. One of the two must be true. But notice in either case, if Q is true, the first conditional is true. And so the disjunction is true. If R is true, then if P, then R is true. And so the second disjunct is true. In either case, this disjunction is true. Okay, so that completes the argument that if the first sentence is true, the second sentence is true. Now I'm just going to go the other way now. Okay, so I won't erase, just so when these slides are posted, everyone can refer back to what I've just done here, but I'll draw a line under to make clear that I'm starting a new thing here. So I'm now going to argue the other way around. So I'm going to argue that if the sentence on the right is true, then the sentence on the left is true. Okay, so suppose the sentence on the right is 1. Okay, that means at least one of those two disjuncts is true. Okay, now I'm going to focus on the left disjunct. The truth is Q and R in these two sentences play symmetric roles. So the fact is, if something is the case about Q, it's going to be the case about R. I don't mean if Q is true, then R is true. I do mean if I reason something about Q and its relation on the right to the something on the other side, on the left, that will also be the case for R. You'll see what I mean in just a second here. So what I'm going to do is I'm going to argue first that if this first disjunct is true, then the sentence on the left is true. Okay? So if the first disjunct is true, the if P then Q, that means either P is false, P is 0, or P is 1 and Q is also 1. Okay, those are the only ways that this could be true. You can't have the case where P is 1 and Q is 0. But in either of those cases, the sentence on the left is true, because if P is 0, again, if P is 0, then this conditional is 1. Okay, that's simple because a conditional is always true when its antecedent is false. Okay, but then on the other hand, in the next row, if Q is 1, then this disjunction is 1, and therefore the conditional here is 1. Okay, in both cases, it's 1. Okay, now I'm gonna, so I only so far was considering what if the disjunct if P then Q on the right, what if that were true? Now, here's what I'm gonna say R and Q play symmetric roles. Is notice the same argument I just used about if P then Q applies to if P then R. If that is true, then either P is false, so the thing on the left is true, or R is true and the thing on the left is true. So it really goes through in the same way that it just went through for if P then Q. Okay, so we're finished. We know these two sentences are logically equivalent. Okay, they have the same truth value in all cases. Now, here comes the fun part. We know that if whenever one sequent is true, whenever one sentence is true, another sentence is true. If that's the case, then that you can prove the second sentence from the first. That's a relation between truth tables and proofs that we can take for granted. What that means is if two sentences are logically equivalent, then in fact, they can both be proven from each other. So in truth, these two sentences here, actually they're proofs going in both directions. And I will tell you as a little advanced hint in case you decide to try to prove these two from each other, and that would be a great exercise to just sit down and say, I'm going to prove the sentence on the right from the sentence on the left and vice versa. I will tell you that going from the right to the left is not so bad. Going from the left to the right is a hard proof. It's one of the hardest proofs of propositional logic. And the reason is because the conclusion on the right is a disjunction, but neither disjunct can be proven from the premise. So if P then Q does not follow from if P then Q or R. Also, if P then R does not follow from if P then Q or R. So somehow you're going to have to prove the disjunction without proving either disjunct. And that's usually a hard proof, that kind of proof. Okay, so what I'm going to do next is I'm going to sketch a proof of the equivalence of these two using the notion of replacement. Okay, there's one last thing I need to convince you of, or at least I'm going to mention before I actually start going through the details, and that is there are some equivalences that you will get familiar with and you'll be able to invoke them all the time. And I'm thinking in particular here of a conditional phi arrow psi is equivalent to a disjunction not phi or psi. Now, if you're skeptical at all, press pause on the video and go write truth tables for both of these, and you'll see the values are always the same. Okay, so that's one thing that we know. Okay, another thing we know is if you just look at this, it also follows that this is equivalent to this. Okay, so the conditional is always equivalent to a negation and disjunction. Okay, so now I'm going to sketch a proof of equivalence of those two sentences we saw with truth tables are equivalent. Okay, so here's what I'll do is I'm going to start with the first one, if P then Q or R. And what I'm going to do is I'm going to string equivalences together here. Okay, so what I'll do is I'll write a triple bar here as if it were an equality to indicate logical equivalence. Okay, and now here's the basic fact about logical equivalence, a basic fact about logical equivalence that you know and can use, and that is if you have a formula, if a subformula of that formula is logically equivalent to something else, then replacing that subformula with the equivalent thing gives you an overall equivalent formulas. That's basically the idea behind replacement. Now, that's not a proof rule, so don't think suddenly now we can greatly liberalize our proof rules. What I'm saying is that is a fact that our proofs, one can prove that our proofs enable that. So the proof rules we already have, that's true, that any two formulas, if they're equivalent, then if you replace, if you have a formula and you have a subformula, and if that subformula is equivalent to something else, you can prove the replaced formula from the first. Okay, this will be more clear as I go through this example. So this triple bar means logical equivalence, but of course it also means interderivability, as you can prove the one from the other and vice versa. Okay, and so here's what I'm going to do is I'm going to first use that equivalence that we saw on the previous page. This is equivalent to not P or Q or R. Okay, now the truth is not P is equivalent to not P or not P. Okay, I haven't convinced you of that. You can also convince yourself of that easily. Write a truth table with not P on one side and not P or not P on the other side. So I'm going to do that replacement here. I'm going to put not P or not P or Q or R. Okay. Now, wonderfully, or is associative. So if you have ors and they're a bunch of ors and they're grouped together with parentheses in a certain way, the parentheses can be shifted around arbitrarily and you'll get something equivalent as long as it's just ors and not anything else. So now we have in this formula on this line, we have or applied to a bunch of atomic sentences and negated atomic sentences. So the fact is I can move those parentheses around. That's one fact. The other fact is or is commutative. That is, if you have something like X or Y, that's logically equivalent to Y or X. Okay, again, you can just quickly write a truth table and check, and truth tables match our proofs. So in other words, X or Y, from that you can prove Y or X, and vice versa. Okay, so now in this case, I'm going to use those, the commutativity and associativity of or a couple times here to move stuff around. Okay, so I'm going to start by pushing the parentheses over here. So that's just the associativity of or. And then what I'm going to do now is I'm going to shift again inside the previous parentheses. Okay, and then I'm going to commute. I'm going to do associativity again. Okay, now in one go on this next line, I'm going to do material conditional twice. So remembering that not P or R is equivalent to if P then R, and not P or Q is equivalent to if P then Q. So I've done really two steps here, and one of replacing formulas with equivalent, logically equivalent formulas, subformulas. Okay, now one last step of commutativity of or. If P then Q, P then R. Okay, so what we've seen here, what I've allowed myself to do is I've allowed myself to replace any subformula with a known logically equivalent subformula. Okay, and then yes, it was not just one or two steps, it was several steps, but I got from originally if P then Q or R, kept moving through equivalences till I got either if P then Q or if P then R. Okay, now we know these are logically equivalent. The first thing and the last thing, we already knew that from truth tables before. Now we see it again in terms of just reasoning through known equivalent formulas. And this actually, what I've just written, could be turned into a proof. Okay, again, if one were to write it out in full, if one literally turned it into basic rules step by step, it would be terribly long. There's going to be a better strategy for proving one of these from the other and vice versa. But this at least gives you the idea of how replacing with equivalents would show that these two formulas are equivalent. Okay, so we'll stop here for today. This gives you a sense of what replacement allows you to do. Also, along the way, we had to get clear on what it means to talk about a subformula of a formula, and we had to get clear on the notion of what it means for two things to be logically equivalent. So I'll just conclude here with a sort of representation on the next page of an abstract representation of what how replacement could function more formally in a written proof. That is, if you have on a line a sentence phi. Now, this notation I'm going to write here is just notation that hopefully expresses an idea, but it's not a formal notation. This notation I've just written says there's a sentence phi with a subformula psi. So psi being in brackets here says it's part of phi. Okay, and now this gamma on the left is some dependency numbers. Who knows what they are? It won't matter. Just there will be dependency numbers there. Okay, and in a formal proof, if you were using replacement, what you could do is on the next line, line N, you could write the formula phi where an instance of phi has been replaced with some logically equivalent. So this is assuming psi prime is logically equivalent to psi. And then there's same dependency numbers gamma. Okay, so this is replacement. And again, it's not a proof rule. It's something I'll convince you later in the course. If you can do this, so when you can do this replacement, there is a proof. So there's, one could stick in between M and N, one could fill out lots of lines possibly, but there's a proof that will get you to that bottom formula, the phi with psi prime replacing psi, from the top formula, from phi where psi is a subformula. Okay, so that's it for today.